All right, let's get into it. Have you ever really wondered what it takes to build a robot from the ground up? I'm talking from the bare metal frame all the way to an AI-powered brain. Well, this is the engineering roadmap you've been looking for. We're going to break down the entire journey, from a simple concept to a fully intelligent system. So why even get into robotics? Because honestly, it's where all the most exciting engineering challenges are happening right now. You see its impact everywhere, from the automated warehouses that power our daily lives to robotic explorers on other planets. This is where mechanical, electrical, and computer engineering all crash together. And let me tell you, the demand for these skills is just exploding. At its heart, a robot is so much more than just a machine. It's a fully integrated system. It has a physical body to act, sensors to perceive the world around it, and a brain to process all that information. And that ability to sense and then adapt its actions, well, that's what really separates a true robot from simple, dumb automation. And if you look under the hood, pretty much every robot follows this exact same architecture. You've got sensors for perception, then cameras or sonars. That data gets fed into a controller, the brain, which could be anything from a simple ESP32 to a powerhouse like an NVIDIA Jetson. The controller then commands the actuators, the muscles, like motors, to move and interact with the world. And the whole thing, of course, is driven by a power system. Now, what's amazing is that this simple blueprint is used to create a huge diversity of machines. You have these massive, super precise industrial arms on assembly lines, you've got mobile rovers exploring distant lands, and you've got increasingly complex humanoid robots. Not to mention these service robots in our hospitals and homes. Each one is just a specialized solution for a specific problem. To really get how robots move, we have to talk about degrees of freedom, or DOF. It's actually a simple concept. It's just the number of independent ways a robot can move. So a 6DOF robotic arm can move its hand to any X, Y, Z point in space, and it can orient itself with any pitch, yaw, or roll. That's what gives it that incredible flexibility to grab and manipulate objects in almost any way imaginable. Building a robot isn't a straight line. It's a cycle. You always start by defining a very clear problem. Then you design the system to solve it. From there, it becomes this constant loop. You build the hardware, you program the logic, and you test it. And crucially, you're debugging and refining at every single stage. This iterative loop is really the heart of good engineering. Okay, let's dive into the skeleton, the mechanical structure. You can break down basically any robot into these fundamental parts. You've got the frame, which provides the stable base. The links are the rigid segments, kind of like the bones in your arm. The joints, like an elbow or wrist, are what allow motion between those links. And finally, you have the end effector. That's the robot's hand, whether it's a gripper, a welder, or a camera. Now, what you build that skeleton out of involves some really important trade-offs. Aluminum gives you a fantastic balance of strength and low weight. Steel, that's for your heavy-duty jobs, where weight isn't the biggest issue. For quick prototypes, nothing beats 3D printing. And for those high-performance applications where every single gram matters, you go with carbon fiber. But yeah, it's going to cost you. So you've got a structure, now you need to make it move. And this is where torque is absolutely critical. Torque is just the rotational version of force. Calculating the torque needed at every joint to lift the robot's own weight, plus whatever it's carrying, that's a non-negotiable step. This calculation is what tells you exactly what size motors you need. If you get this wrong, your robot will be underpowered and it just won't work. But how do you control that movement with any precision? That's where we get into kinematics. Forward kinematics is the easy part. If you know all your joint angles, you can easily calculate where the robot's hand is. But what we usually need is the opposite, inverse kinematics. We know where we want the hand to be, and we have to figure out the complex set of joint angles to get it there. That's a much harder math problem, but it's essential for any useful task. Before you ever cut a single piece of metal, you build the entire robot virtually. Computer-aided design, or CAD, is fundamental. It lets you model every single part, check that they all fit together, simulate the robot's full range of motion, and even run stress analysis to find weak points before they become a real problem. This design twice, build once philosophy will save you a ton of time and money. A great mechanical design is also a safe and stable one. This means you have to design for a low center of gravity. And you have to make sure it always stays within the robot's base of support to keep it from tipping over. You also need to distribute loads properly and, this is a big one, plan for failure by designing in things like mechanical stops and software safety limits. All right, moving into the electronics, the power system is basically the robot's lifeblood. You have to choose a battery chemistry, like lithium polymer for its awesome power density, and then design a system to regulate that power. Your motors might need 12 volts, but your delicate logic circuits need a clean 5 volts. Doing a detailed power budget is absolutely essential to make sure you pick a battery that's big enough. Next up, the brain. Your choice of controller completely depends on how complex your robot is. An Arduino, perfect for simple control tasks. An ESP32 adds wireless capabilities, which is huge. For more complex logic or running a full operating system, a Raspberry Pi is a great choice. And when you need to do heavy lifting, like real-time AI and computer vision, you bring in a GPU-accelerated beast like the Jetson Nano. The controller's commands get carried out by the motors. For robotic joints that need to hold a specific angle, servo motors are your go-to. For simple wheeled robots, you'll see a lot of basic DC motors. Stepper motors are great when you need precise, repeatable movements. And for high-performance stuff like drones or advanced arms, you'll find brushless motors. Now, here's a critical detail. You can't just plug a power-hungry motor directly into your microcontroller. It would fry it instantly. The solution is a motor driver. This little circuit acts like an electronic switch. It takes a tiny signal from the controller and uses it to manage a much higher current for the motor. Circuits like the L293D H-bridge are classics that let you control both direction and speed. For a robot to be smart, it has to be able to sense its environment. A camera gives it vision, an inertial measurement unit, an IMU, gives it a sense of balance and orientation. And things like ultrasonic or infrared sensors let it measure distances to avoid bumping into things. These are, quite literally, the robot's eyes and ears. All these different parts, the controller, the sensors, the motor drivers, they all need to talk to each other. On the robot itself, this usually happens over fast wired connections like I2C or SPI. And for talking to the outside world, for remote controllers sending data, you'll use wireless standards like Wi-Fi and Bluetooth. When you're first wiring everything up and just trying to get things to work, a breadboard is your best friend. It lets you plug things in and change them around super easily. But for a final product that's reliable, compact, and robust, you graduate from the breadboard to designing a custom printed circuit board, or PCB. That's the professional standard. Okay, let's talk about the software that makes this all come alive. Embedded programming is all about writing super efficient code that runs directly on the hardware. C and C++ are the industry standard because they're fast. The core logic is almost always this continuous loop. Read your sensors, process that data, then actuate your motors. And this has to happen incredibly fast. We're talking real time. So how do we make that control precise? Well, open-loop control is like throwing a ball at a target with your eyes closed. You just send a command and hope for the best. Closed-loop control is where the real magic is. You use sensor feedback to see what actually happened, compare it to what you wanted to happen, and then make constant corrections. That feedback loop is the absolute key to any high-performance robot. And the workhorse algorithm for that closed-loop control is called PID. It stands for proportional, integral, and derivative. Basically, it calculates a correction based on how far off you are right now, how much error has been building up over time, and how fast that error is changing. By tuning these three values, you can get a system that's both lightning fast and rock-solid stable. When you apply that control to navigation, you get path planning. At the simplest level, you have a line-following robot that just reacts to sensors to stay on a line. A step up from that is basic obstacle avoidance. And at the high end, you have complex algorithms like A*, which can actually look at a map and compute the most efficient path from point A to point B. You can imagine as robots get more complex, the software can become a total nightmare to manage. That's exactly why the Robot Operating System, or ROS, was invented. It's a framework that lets you break your entire system down into small, independent programs called nodes that all talk to each other. It has become the industry and research standard for a very good reason. And this brings us to the really cutting-edge stuff, artificial intelligence. The most common use in robotics today is computer vision. You can run powerful deep learning models like YOLO 5 on a GPU-accelerated board like the Jetson Nano to detect and identify objects in real time. This gives the robot a genuine understanding of what it's seeing, which unlocks a whole new level of intelligent behavior. So let's put it all together with a classic starter project, a line follower. The mechanical build is super simple, just a two-wheeled chassis. The electronics are just an Arduino, a motor driver, and a few infrared sensors. And the program is a basic closed-loop system that just adjusts the wheel speeds to keep the robot on the line. It's simple, but it teaches you all the core principles. Now, let's look at a more advanced example, a robotic arm. Here, the mechanical challenge is all about precision assembly. The electrical challenge is providing stable, reliable power to all those servos. And the biggest challenge, by far, is in the software. You have to implement those complex inverse kinematics equations we talked about to control the arm with any accuracy. I promise you, you will spend most of your time debugging, so you need a good strategy. Rule number 1 is this: test every single component in isolation before you put them together. Get the motor spinning by itself. Use a multimeter to check your hardware. And use simple print statements in your code to see what the robot is thinking. It's a lifesaver. And here are the traps that almost everyone falls into at first. Picking motors that are way too weak. Not providing enough power, which causes your robot to randomly reset. Having bad ground connections, which creates all sorts of electrical noise and weird behavior. And the biggest one, trying to build something way too complicated for your first project. Start simple. Trust me. All of this leads to what I call the final boss of any robotics project: system integration. This is the phase where the mechanical, the electrical, and the software systems, all the things you've built and tested separately, have to finally come together and work as one. It is without a doubt the most difficult phase, but it's also the moment your creation actually becomes a robot. Okay, let's touch on a few advanced topics. For a robot to be truly autonomous, it needs to navigate places it's never been before. The core technology for that is called SLAM, simultaneous localization and mapping. It's this classic chicken and egg problem. To build a map, you need to know where you are. But to know where you are, you need a map. SLAM algorithms are what solve both of those problems at the same time. Now, as robots move out of cages and factories and into our world, we have to think really carefully about how we interact with them. This field, human-robot interaction, is all about designing that interface. It's about making robots safe, intuitive, and easy to work with. This is what's leading to cobots, collaborative robots that can work right alongside people. Another totally fascinating area is swarm robotics. So instead of one big, expensive, complex robot, you use a whole fleet of many simple, cheap ones. There's no central leader. Each little robot just follows a few basic rules, and out of those simple interactions, incredibly complex group behavior emerges. Think of an ant colony. It's the same idea. And all this brings us to a final, really critical question. As engineers, we're building systems that can sense, think, and act on their own. As these systems get more and more autonomous, we have to start asking ourselves, where does our responsibility begin and end? Answering that is the challenge that's going to define the entire future of this field.